All right. Let's talk about some integration over generalized regions. All right. So we've been moving kind of fast through these sections, and I realized that we went over 12.1 and actually 12.2 last class period. So I actually went through 2 sections instead of 1. So last class was 12.1 and 12.2. So now we're going to be talking about 12.3. This is double integrals. Over general regions. All right. So a little bit of 12.2 is the concept of the iterated integral. So for instance, let's say you have some function x. Let's say we have some function xy, and we iteratively integrate it. Let's say dx, dy, dx, dy. This is called an iterated integral. All right. Notice that something like this can become x squared, y, everything over 2. Integral, integral, integral. Now we got a dy, a dx, and another dy. Notice that then we can iterate the integral again. This becomes integral, integral x squared, y squared, everything over 4, dx, dy. We can integrate it again. We get integral of x cubed, y squared, everything divided by 12, dy. Iterated again, integrated again. So I got x cubed, y cubed, everything over 3 times 12, which is 36. And you know, there's some plus c's there, but we can set all the plus c's equal to 0. Okay. So this is the concept of the iterated integral. You just do the integral over and over again. Now, let's talk about the double integrals over generalized regions here. Okay. So let's say I have a 2-dimensional picture here. Let's say I have some region right here. Let's call it D for domain. All right. Let's say we want to integrate a three-dimensional function on this domain, but notice it's irregular and it's hard to define where it's at. But what we can do is we can encapture this region inside a rectangle, call it R. Okay, so then if what's inside here is some f of x, y, we can define a new piecewise defined function, capital F of x, y. It can be defined piecewise as outputting f of x, y if our x, y is an element of D, and have it output 0 if our x, y is an element of R and simultaneously x, y is not an element. I mean, it's an element of D. It's 0 if it's an element of R and not an element of D. That's what I'm trying to say here. Meaning the function outputs a 0 here. It's an element of R, but it's not in D. So capital F of x, y will equal 0. And here, capital F of x, y will equal lower f of x, y, lowercase f of x, y. So when we define a function like so, what is the importance of this? Well, the importance of this is because now we can integrate over any kind of weird region like this D, meaning that the integral, the double integral over the region D of f of xy dA can now be equivalently expressed as the double integral over the region R of capital F of xy dA. Okay, so this is what this new way of thinking buys us. And it has to do with defining capital F of xy like so. So let's see why this is even important or interesting. Let's think about this in 3 dimensions. Let's say you have some surface. It casts a shadow. All right. Over here, here's our f of xy is equal to a z. But notice we can transform this, and this is our actual domain D. All right. This is the 2-dimensional domain. The output is the 3rd dimension Z. But notice if we define using our new way of doing it, here's our blob over here. Here's a shadow that the blob casts. We can actually keep that region enclosed in a region R. This is some region D. And now this, instead of being lowercase f of xy, is capital F of xy equaling Z. So this is kind of like the theoretical framework. All right? That's why we did this to begin with. All right. Now, let's discuss what a type 1 region of integration is. All right. A type 1 region is defined by domains D that look like this. They're the set of xy, an element of R2, such that x ranges from A to B and y ranges from C to D. All right. But our C to D will actually be replaced with a function to output those values. So this will be our G1 of x, and this will be our G2 of x. That is the main difference. They're still numbers, but they're the outputs of a function, G. What does that mean? Well, G1 and G2 are functions that map A to B onto the reals. So they're continuous value functions. And what do? They allow us to parameterize the location of a surface D. Let's call this D, all right? Let's bring this down here. Here's our A. Let's bring this down here. Here's our B, okay? We can say that this top curve is y is equal to G1 of x. I mean G2 of x, it's the larger one. And over here, this bottom curve is our y is equal to G1 of x. All right. This is a type 1 region. When the boundaries of your surface are defined by a function above all of the region's surface and the function below all of the region's surface. Okay? So whenever you do this, we got a region R that we can cover this guy with. So we'll call this region R. Let's define R. All right. Do we want to do it set theoretically? We can just do it by interval notation. It is some AB cross some CD. It is just a Cartesian product of 2 intervals. Meaning, if I have this is right here C, over here this is D, and this is A and this is B. Maybe I'm gonna want to contract this a little bit over here like that. There we go. And maybe have this little bit cut off like that, so it's right at B. You get what I'm saying here? All right. That's how we define that. And this contains the region D. So we can integrate our function on the new region that contains our other region. Okay. All right. So meaning that the double integral on the region D of our f of xy, differential A, is the same thing as the double integral on the region R of our capital f of xy, as we defined earlier, differential A. And differential A is actually the same thing as the product of dy dx. Because remember last class, dy dx is defined as an area element. It's a differential piece of area. Remember the piecewise defined function that I deleted. This implies this is equal to 0 if y ends up being greater than g2 of x, or y being less than g1 of x. So this is a type 1 region. So why don't we do some concrete examples here? That's the general abstract argument. Why don't we do some concrete examples? I need to clear up some real estate here. Let's calculate the integral from calculate the integral on some region D of some x plus 2y dh, okay? Where D is defined to be the region bounded by the parabolas y is equal to 2x squared and y is equal to 1 plus x squared. I just can't live with this. I can't live with the way that looks. Okay, so how about we make it look like this? All right. Have a look like that. So we're interested in taking the integral of this region right here. Where are these 2 points where they touch? Well, it's merely the points where these are equal. Okay? Notice that this implies I get x squared is equal to 1, which implies x is equal to plus or minus 1. So f of plus or minus 1 are these locations. So this is at 1 and f of 1, which is either one of these, which is 2. And this is negative 1, 2. All right? Those are our spots. So this is indeed a type 1 region where this right here is given by our function over here. And this right here is given by our function over here. We can see that it's bounded above and below by 2 functions that capture where we want to integrate. Okay, so this is going to become this following integral. This right here is going to be the same as this integral right here. Okay, where is it at y? Well, y is parameterized by your g1 of x, your g2 of x, and this is your a to b, right, in general. Then we'll bring the general integral and create a concrete. So for x, it ranges from 1 to 1, from here to here. For y, it ranges from this function, 2x squared, to that function, 1 plus x squared. And what we want to integrate is this. And it's going to be a dy dx. we integrate with respect to y first. Okay? So then this equals the integral, all right, here. And then we're just going to do integrate with dy. So this becomes x, y plus 2y squared from y equals to 2x squared to y equals 1 plus x squared x. So then this ends up equaling the integral from -1 to 1 of, I replace with every y what we have evaluated. So x, 2x squared plus, wait a second here, did I integrate this right? 2y squared over 2, so these 2's cancel, right? And so then this becomes 2x squared, everything squared, quantity squared. That's this piece. And then we got to evaluate it. So this becomes x, 1 plus x squared, plus our 1 plus x squared, quantity squared, close it up, dx. All right. So then this integral breaks down to the integral from -1 to 1. Let's see what all that says. So this is 2x cubed plus 4x to the 4th minus our x plus x cubed plus our x to the 4th plus 2x squared plus 1 dx. Because this times this is x squared, this times that is x cubed, plus our factoring binomial 1 plus x squared, quantity squared. That gives me 1 plus 2x squared plus x to the 4th, everything dx. Let me distribute this minus now. Distribute the minus to each term. And make this a plus. Now we can do some cancellation here. All right, we got x to the 4th. You got this integral -1 to 1 of -x to the 4th. With this x to the 4th gives me just 3x to the 4th. Where's the x cubes at? Where are the x cubes at? The x cubed here, x cubed here. Then I get plus x cubed over here when they cancel out. What about the squares? We got a -2x squared, cancel. And then a minus a 1, dx, okay? So, moving the integral upstairs, we integrate, so this becomes 3x to the 5th all over 5, plus x to the 4th all over 4, minus 2x cubed all over 3, minus x, everything evaluated from -1 to 1. And whenever you perform this operation, what do you get here? Oh, and I needed to put a negative here, and I needed to put a negative here. I accidentally put that there. Negative there, negative there. This needs to be a positive, and this needs to be a positive. Where did I mess up the calculation here? I had messed up a minus sign. So when we fix that, so this needs to actually have a negative on it. This needs to have a negative on it. Over there, that needed to be positive. And this remains positive, right? Two, right, okay. So then this ends up actually, once you evaluate it, equaling to 32 over 15. Okay. And I actually forgot to incorporate this minus x over here. So let me actually reproduce this with the minus x there. Forgot to include that term over here. So when we integrate it, we get negative 3 over 5 x to the 5th minus x to the 4th over 4 plus 2 over 3 x cubed plus x squared over 2 plus x evaluated at x equals negative 1 to 1. When you do that computation, it equals 32 over 15. There we go. So that value, 32 over 15, is indeed the integral of this shaded region right here. All right. So that was a type 1 situation. Okay. Let me see here. What about the volume of a solid given by the intersection of these two curves? All right, say this one is y is equal to x squared, and this one is y is equal to 2x. All right, we aspire to find what is the yellow shaded region. What is the integral of this yellow shaded region in between the two functions? Okay. All right. And not only that, but in this problem, we want to find the volume of the solid that lies under the paraboloid given by z is equal to x squared plus y squared. And move this and what's up here? And above the region D in the XY plane. Where over here, this is our region D in the yellow. All right, so notice that this is an area, and the problem is saying, okay, we want to find what is the volume whenever you extend this out into the third dimension in reference to this paraboloid z is equal to x squared plus y squared, okay? So we notice that they touch here at 2, 4. You can discover that by setting the two functions equal to each other. X squared is equal to 2x. That means x is equal to 2. All right. And then f of any of these, f of 2 is the same thing as 2 squared, which is 4. So they meet at 2, 4. And actually, they also meet at 0, 0 and 2, 4. So this is a type 1 region because this domain is bounded by this function y is equal to x squared from the bottom and bounded by this function y is equal to 2x from the top. So we can define our domain region D as the set of all xy an element of R2 such that x ranges from 2 to 0 and y ranges from 4 to 0. And not only that, but we can actually parameterize 0 and 4 continuously for all inputs of x, meaning down here at x squared and over here at 2x. That is the rub of this argument, okay? Because now I can say the integral over the region of f of x, y, differential area element, is the same thing as the integral of, let's say, 0 to 2 of x squared to 2y of our function of interest x squared plus y squared dy dx. Okay, and then we just integrate. This becomes the integral of 0 to 2. This reduces to a x squared y plus a y cubed over 3. Evaluate it at y is equal to x squared, y is equal to 2x dx. And then this equals 0 to 2. I should probably not have that integral here because I'll run out of space. So this equals integral from 0 to 2 of, let's evaluate. This becomes x squared times 2x plus 2x cubed over 3. Everything subtracted by x squared times x squared plus x squared cubed over 3 dx. So the reason that this setup works is because the area, the cross-sectional area is parameterized now. And when we complete the integral, it calculates the column, the volume column that you form with the paraboloid in 3 dimensions. So this is why the end result of what we're doing is going to result in a volume, okay? Moving the calculation over here, that results to the integral from 0 to 2 of 2x cubed plus 8x cubed over 3 minus x to the 4th minus x to the 6 over 3 dx, okay? And then you integrate again, all right? But before we do that, we got to establish a common denominator and group some like terms, right? Okay. So then this reduces down when we calculate the integral. Like so. And when you evaluate it, it ends up becoming 216 divided by 35. Okay. That was type 1. It is not so dissimilar to a type 2. Type 1 has functions parameterizing the vertical values from the top and bottom. Guess what a type 2 does? It has functions that parameterize the horizontal changes of your domain region, as you will see what I mean here in a second. Okay. So let's say you have a domain, but it looks kind of like this. All right. So here's our D, here's our C, here's our capital D. So we can have functions right here. This function would be some h1 of y on the left, and this function over here will be some h2 of y right here, and right along here. All right. So now our D is defined as the set of all x, y, an element of R2, such that now y is bounded above by D, bounded below by C, and now x is the one that has the interesting parameterization. It's bounded to the left by h1y and to the right by h2y. Close the sets. So then our integral over D of f of x, y, dA, what does that end up becoming? Well, it just becomes integral from C to D, integral from your h1x to h2x, f of x, y, x, dy. Notice how that's different than a type 1, where you start off with dy instead of dx. Now dx comes first. No cell phones in class. Okay. Let's actually do an example of a type 2. Let's say we have a situation like this. Let's say we have a bounded region D right here. It's bounded by a function y is equal to negative square root of 2x plus 6. That's this part right here. Okay. And over here up top, this is y is equal to positive 2x plus 6. All right. And over here, this is the function y is equal to x minus 1. Okay. And I really haven't drawn this appropriately. Actually, I need to redo the drawing because I have it going through the wrong y-intercept. I have it going through the wrong y-intercept. So here's x, y. So then we want to have it going through here. This is x, 0, negative 1. Then we want to have our function coming through like this, and like this, and like that. So this intersection point is 5, 4. This over here is at 0, negative 3. This we know what it is, all right? Very good. So the top function is still that. The bottom function is still the negative of that 2x plus 6. And this is still our y is equal to x. Minus a 1. Because it has a y-intercept of negative 1, okay? We want to calculate the integral of this region. Okay. It's a type 2 region, so we're going to have a type 2 double integral. Okay. So let's say we have this region here, and we want D to be defined as the bounded region by y is equal to x plus 1, and y is equal to, and y squared is equal to 2x plus 6. Hence why we get the square root of plus or minus. Okay. Furthermore, what we want to actually calculate is the double integral over the xy of the dk, with this as our boundary D. So we want to integrate xy with the boundary D. Okay? So our integral becomes the integral from negative 2 to 4, integral from 1/2 y squared minus 3 to y plus 1 of our xy dx dy, because we're moving from left to right. And the parameterization for the parabola comes first, and the line comes second, because the line is on the right, the parabola is on the left. Notice that what's on top is really when you solve for y and you get y is equal to x plus 1. And what's on bottom is what happens when you solve for y here, okay? I mean, solve for x. Over here, we're going to solve for x. So over here, when you solve for x, we get x is equal to y plus 1, and hence why it comes over here, y plus 1. Over here, when we solve for x, we subtract the 6, so I get y squared minus 6 is equal to 2x, and I divide by 2, and I get x is equal to 1/2 y squared minus 3. And that is why this appears over here. Because we want to integrate from left to right horizontally dx, we have to parameterize these as functions of y. Because a type 2 had, over here, it had some h1 of y, some h2 of y, and some c and d, some f of x, y, x, dy, right? So we had to express our functions in variables purely in y. That's why we did the algebraic manipulations that we did so far. And then we just integrate. This becomes, and last but not least, this -2 and -4 limits of integration are based off of the fact that that is where the function ranges from top to bottom. Okay? From top to bottom and from left to right. Notice that the second integral is a dy. And so that the lowest value that this function assumes is this at -2, y equals -2. And the highest value it assumes is that y is equal to 4. You can easily calculate why that's the case. So that's why our limits of integration for y are the lower and upper bounds of the region D. Okay? Then we just compute the integral. So this becomes integral of -2 to 4 of x squared y, evaluated at x is equal to y plus 1, x is equal to 1/2 y squared minus 3 dy. So this equals the integral of -2 to 4 of our y plus 1 squared y minus our 1/2 y squared minus 3 squared dy. Okay? Once we compute that integral and we compute, let's see here, what we end up getting is this ends up equaling 1/2 integral from -2 to 4 of -y to the 5th over 4 plus a 4y cubed plus a 2y squared minus a 8y dy. And guess what? I will say that this is college and you must fill in the rest of the steps. They do that to all of us. Because the time is short and I have to get to the last piece of information on the lecture. Okay? So then this ends up equaling, when we integrate with respect to y, okay? And when you evaluate that, this ends up working out to be equaling 36. Okay? That is all. Make sure you know how to do the type 1 and type 2 situation, because some integrals are easier using a type 1 versus a type 2. So on the exam coming up for this section, you have to be aware of which type of surface you want to treat it like in order to make your computation more simple. Because notice we could have treated the same problem here Let me draw this again. Okay. We could have treated this as integrating vertically, all right? Then our integral would be set up like so. Then we'd go from -3 to -1, and the integral from negative root 2x plus 6 to positive root 2x plus 6 of our xy dy dx. It's wide because now we're parametrizing from top to bottom. And notice the dx starts at -3 and -1, and that's due to the fact that if you draw one piece, you go to there, okay? But then you must also add it to another piece, and it's getting really cluttered. So I'm gonna redo the integral because it's very cluttered over there. Redoing that integral, it ends up equaling a two-part integral, which is much more difficult to evaluate. All right, this is your dy dx, but then you have to add it to another double integral. Okay, so choose how you want to evaluate your surface carefully, because the integral we did earlier was much easier to evaluate than this integral would. Not, you're doing two double integrals instead of one. Okay? The limits of integration are obvious when you consider drawing it appropriately. I drew it really quickly and it's not really as good as it should look. But this intercept right here is at 3, at -3. Hence why it starts off at -3, -1. Okay. Let me know if you guys have any questions.